Hi everyone. In this video we are going to look at a couple more examples of molecules and predict their polarity. The first one that we're going to look at is carbon tetrafluoride, CF4. We can build a Lewis structure. My central atom will be carbon, and this Lewis structure is just a planar representation of the three-dimensional structure. So we would identify our polar bonds next. We know that fluorine is the most electronegative element, so we'll have 4 polar bonds as such. And then we need to think about the molecular geometry. Carbon with 4 electron domains will have electron domain geometry of tetrahedral. All of those domains are bonding domains, so the molecular geometry will also be tetrahedral. So let's draw this in a more representative way of the three-dimensional structure. We can use our dashed and wedge notation. So we end up with that as the three-dimensional picture. We can draw on our bond dipoles just to be able to see those again. And so in this case, it is a little bit more difficult to see this. So now we need to think about whether or not these bond dipoles will cancel or not. So what I'm going to do is break it down a little bit more. So we can say that, well, this is coming out of the, behind the board, and this is coming out of the board. So these are going to have a net dipole kind of in this direction, right? And then these guys going up and over are going to have a net dipole in this direction. And those guys are going to be equal and opposite. All of these atoms are identical, so the pole will be equivalent. And since they are opposite, they will cancel each other out. Now, if we imagine changing one of these to a different element, we would then create a polar molecule, because the dipoles would no longer be equivalent. They would still be pulling in opposite directions, but with different magnitudes. And so we could create a polar molecule by changing any one of those. We could, in fact, change up to 3 of those fluorines and have a polar molecule. Now let's look at something that has lone pairs on the central atom. Take ammonia. We can draw the Lewis structure as such, thinking about the molecular geometry. And, well, before we do that, let's do our polar bonds. Nitrogen is more electronegative than hydrogen, so we will have my polar bonds in the direction of that nitrogen atom. We have 4 electron domains. We have those 3 bonding groups in the lone pair. So that would be electronically tetrahedral. But when we look at the bonding groups by themselves, we would get a trigonal pyramidal geometry, right? And to better represent that in 3 dimensions, we can use the wedge and dash notation again and indicate my polar bonds. Now these polar bonds are all going in the direction of the nitrogen, kind of in that upward direction. So when we think about will these bonds cancel, the answer is no. They're all going in one net direction, so that my molecular dipole, this pink arrow, will be in the north as it's drawn here on the board. Okay, so ammonia would be polar. Let's look at a slight variation on this. Let's look at NF3. So skipping ahead to the 3-dimensional structure, we'll have something that looks almost the same as this. Now we have to think about the electronegativities. Now we're going to have the dipoles in the opposite direction, right? Because fluorine now is more electronegative than nitrogen. And so when we think about adding these vectors together, we have a net molecular dipole in the south direction, as I've drawn it here. Of course, you can orient this molecule a number of different ways, and you can have that molecular dipole pointing in many different directions. But in this case, we have it as noted. And so I just wanted to do this to highlight the fact that we are not always going to be pointing that dipole moment in the direction of that lone pair. And that's kind of one misconception that I want to point out that in the case of ammonia, it does, but in the case of the nitrogen trifluoride, it does not. It just depends on what atoms are connected there and the electronegativities of those atoms. The last thing that we're going to look at in terms of polarity in molecules is with respect to organic compounds. So I've drawn two organic compounds up here. They both contain some polar bonds and some nonpolar bonds, and we are going to have to evaluate whether or not this molecule overall is polar. So we're going to take the same steps. We want to make sure we have a structure, identify my polar bonds. So I look, okay, I have carbon-carbon bonds, that's two identical elements that will be nonpolar. I have carbon-hydrogen bonds, those are nonpolar. And then I have carbon-chlorine bonds, and those would be a polar bond. So I've got my two polar bonds, and I might as well just do the same in this structure now. Got two polar bonds. And then I would think about the molecular geometry. So at this carbon, it is going to have three domains. So we'll have trigonal planar, electron domain geometry, and molecular geometry. Same thing here, here, and here. They all have the same geometry. So these are planar and flat molecules, and that is easily represented here on the two-dimensional board. And so we see pretty much more or less what the molecule actually looks like. So now we have to determine whether or not these bond dipoles will cancel. So we want to say, okay, well, these are the same kind of bonds, so the pole would be equivalent, and then are they opposite of one another? Yes, they are opposite of one another. So this would be a nonpolar molecule. And then in the case here, we are going to be looking at, okay, we have the same pole, but they are not going opposite each other. They're going in the same net direction. So I have a molecular dipole as such, and this would be a polar molecule. So we can do this for just about any kind of compound. As long as we have the structure, we can determine whether or not it's polar. So try some practice problems with this, and thank you for watching.